This lesson deals with the BJT as a circuit element. You can find these notes in the ECE302 ebook in Chapter 3, starting on page 22. In our last video, we did a piecewise linear model for a BJT. We had 3 models in the forward mode, and we had 3 models in the inverse mode. These 6 piecewise linear models cover all of the VI characteristics, and so the transistor must be in one of those 6 states. Like a diode, we can assume a state and then look for contradictions. Consider this example where I have 1 BJT, 2 resistors, and 2 batteries. And for the transistor, let's assume that I sub S is 0.1 femtoamp, beta F is 100, eta F is 1, beta R is 1, and eta R is 1. These are actually the default values in place. Let's determine the state of Q1. In order to do that, we need to know what VBE on is and what VCE sat is, because we know what beta F is. If we're not given any other information, let's assume that VBE on is 0.7 and VCE sat is 0.2. If we were to guess the inverse mode, let's assume that the base collector on voltage is 0.72 and that the collector emitter saturation voltage is minus 0.02. Let's just take random guesses and see what kind of results we get, and then we can take a look at maybe a generalization of guessing. Perhaps the simplest model is cutoff, so let's start with that one. Let's assume that the transistor is in cutoff, and that means there's an open circuit between the base and the emitter and between the collector and the emitter. That means that the current here is 0 and the current here is 0. I need to show that the base emitter is less than or equal to 0.7 and that the collector emitter is greater than or equal to 0. Let's go around the loop. Rising voltage is 5. The drop is 56K times 0 plus the base emitter voltage. The base emitter voltage then is equal to 5 volts. But that isn't less than 0.7, so that's a contradiction. We could stop right here because this can't be the correct state. But let's finish it up and solve for the collector emitter voltage. Rising voltage is 15. The drop is 0 times 1K plus the collector emitter. That makes the collector and emitter just 15 volts, and that is not contradicted. But we still are not in cutoff. Let's guess the next simplest model, which is saturation. Take the transistor out. We'll put between the base and emitter VBE on, which we're assuming to be 0.7, and between the collector and the emitter VCE sat, which we're assuming to be 0.2. We need to show that the base current and the collector current are greater than or equal to 0, and that the ratio of IC to IB is less than or equal to beta F. Current coming in here in the base is the current in the 56K resistor, which should be the voltage across it divided by 56K. That's 5 volts minus 0.7 over 56K. That's 77 microamps, and that is greater than or equal to 0, so that checks. The collector current is also the current in this 1K resistor. And let's take the difference of 2 node voltages. 15 volts minus 0.2 divided by 1K is 14.8 milliamps, and that's also greater than or equal to 0. But what about their ratio? Their ratio is 192. That needs to be less than or equal to beta F, but it's not. It's greater than. This is not in saturation. The other model in the first quadrant, or the forward mode, is the active region. Let's assume that one next. We'll replace the transistor by its model. Between the base and emitter is a battery of 0.7, VBE on, and between the collector and the emitter there's a current-controlled current source that is beta FIB. Here's I sub B, and then beta F times that, and that would be our collector current. I need to show that I sub B is greater than or equal to 0, and that the collector emitter voltage is greater than or equal to VCE sat. The current coming in here is the same as in our last case. We have 5 volts minus 0.7 divided by 56K, 77 microamps, and that is greater than or equal to 0. The current that's in the collector, though, is going to be beta F times that base current. 100 times that is 7.7 milliamps. And now I can solve for the voltage across here. The rising voltage is 15. The drop is 7.7 milliamps times 1K plus the collector emitter voltage. I can solve for that. That's going to be 15 minus 7.7 volts, and that's 7.3, and that is greater than or equal to VCE sat, which was 0.2. This is in the active region. There is only one possible state, and we found it. Suppose we go back and repeat this example, but now beta F increases to, say, 300. Now let's go back to page 23, the last page. Our I sub B would still be the same. Our I sub C would still be the same, but now the ratio, which is the same, is now less than beta F because beta F is 300. So this would have been the correct state. Would this last one have been contradicted? Well, let's see. I've got I sub B as 77 microamps, but now I sub C is 300 times I sub B, and that's 23.1 milliamps. When we solve for the collector emitter voltage, that value of I sub C is going to produce a negative voltage across the collector emitter. But that's not greater than or equal to 0.2, it's actually less, so then it's not active. There is only one possible state given the parameters of the transistor. Suppose that our battery begins to decay. In other words, the value begins to drop. Where is the edge of saturation? Let's put the model in for the edge of saturation for our transistor. We're going to replace this by its model. Between the base and the emitter, we'll have our VBE on of 0.7. Between the collector and the emitter, our VCE sat of 0.2. But now we're going to label that the current is 100 I sub B. In other words, beta F I sub B. I still need to check that the base current is positive, and then I can solve for the value of VCC. Please note that what we've done here is we've overspecified the conditions of the transistor by one more term, by adding this in. We have to back off on one parameter. If we don't do that, we won't get a unique solution to our problem. Our base current is the same as before because it's still 5 minus 0.7 over 56K. And 100 times that is still 7.7 milliamps. Now we can solve for the battery. The rise in voltage equals the drops around the loop. 100 I sub B, which is 7.7 milliamps times 1K, plus 0.2 has to equal the battery VCC, and that's 7.9 volts. This battery could start out at 15 volts and begin to decay and drop down to 7.9 and still be in the active region. As we saw with diodes, taking random guesses can take forever to solve a problem. Well, is there some strategy we can use with BJTs for making a better guess on our first shot, or maybe the second shot? I'll describe the following for an NPN transistor, but the P and P will be the words that are in the square brackets. Take a look at your circuit and see if current wants to flow into the base, and if it does want to flow in the base, well then it can't be cut off. It's got to either be saturated or active. To be active, the collector current has to be equal to beta FIB. If I have a collector resistor, if that resistor is too big, then I can't draw enough current. If we had currents on the order of milliamps, once we get into large K ohms, we would drop too much voltage across the resistor. It can't be bigger than the battery that we have. So if I see a 20K resistor in the collector, I'm going to probably guess saturation for my first shot. Likewise, if I see a base resistor that's too small, and if I get base currents that are in the milliamp range, well then, again, we can't draw enough current in the collector to go active. If I see a resistor that's maybe smaller than 1K, I would probably guess saturation for my first guess. If an application is labeled as amplifier, then the only guess that will work is actually the active region because we can't amplify anywhere else. I'll show this in Chapter 5. If the application is a switch or a logic element, then it's going to be in saturation if we've got base current. We'll see that a little bit later in the chapter. Lastly, the inverse modes. These are rare. There's only a few applications where we actually are driven into the reverse mode or inverse mode. I'd only guess this mode if the cutoff, active, or saturation models yield contradictions. Let's solve the same problem using a load line approach. Since we're given the SPICE parameters, let's generate the VI characteristics of the transistor. In other words, the base emitter voltage versus the base current, and the collector emitter voltage versus the collector current. And we can use the load lines on top of those pictures to figure out the operating point. We've done the collector current versus the collector emitter voltage previously. Let me vary the voltage between the collector emitter between 0 and 15 volts, and let me put 2,000 data points here. So divide this by 2,000 and you get 7.5 millivolts. And I'll do that for each value of I sub B, and I'll take steps of 15 microamps. We'll do 11 steps here, from 0 to 150 microamps in 15 microamp steps. For the base emitter side, what I want to do now is vary the base current from 0 to 150 microamps, but now in a lot of data points. So I'll do 2,000 data points here. So divide this by 2,000, I get 75 nanoamps. I'm going to do that for 16 values of the collector emitter voltage, going from 0 to 15 in 1 volt steps. The pictures are on the next page. What are the load lines going to be? Well, I need to write an equation around this loop. The rise in voltage is 5, the drop is 56K, which is the value of R sub B, plus the base emitter voltage. And that's this equation over here. So I can solve for I sub B as a function of VBE. Bring this on the other side of the equation, so I get a minus VBE, divide by 56K, and then divide the 5 by 56K. I have the equation of a straight line, where I'm plotting this on the y-axis and this on the x-axis. For the collector emitter, the rise in voltage is 15, the drop is I sub C times 1K, plus the collector emitter voltage. And that's the equation on the bottom of the page. Solve for I sub C. Bring this on the other side of the equation as a minus VCE, and divide by 1K, and then divide 1K by the 15. And again, we have the y-axis and the x-axis and the equation of a straight line. Note something new here, that as we varied the collector emitter voltage, we actually got a family of curves. There's actually quite a few curves between 0 and 1. I did 1 volt steps. There's a lot of curves here, but they just basically become one curve once you get to about 1 volt or so. Let's take our equation from the previous page and find the x and y intercepts. From the previous page, if we were to set I sub B equal to 0, then the base emitter voltage would just be equal to 5 volts. That's not the solution, but just simply 1 point here. And if we take our other equation for I sub B and let VBE equal 0, then I sub B would be 5 volts over 56K or 89 microamps. That's this point right over here. So we draw a straight line. This is all possible solutions for that battery and resistor on the base side. It runs into these curves in multiple places. I'll explain why I picked this one just a little bit. Let's also do the load line on the collector emitter voltage versus collector current and do the same thing. We'll take the intercepts. If we were to take our equation on the previous page and set I sub C equal to 0, we would get that VCE is equal to 15 volts, which is 1 point on a straight line. And then from the other equation, if we were to set VCE equal to 0, we would get I sub C is equal to 15 divided by 1K. So that's our all possible solutions. And of course, these are the all possible solutions of the transistor. Let's go back to this previous curve. Could we be on this line over here? Well, when the collector emitter is 0, we're over here, and there is no intersection with the VI characteristics. So this must be the solution. That'd be our first point, and that's saying that the value of the base current is about 75 microamps, and the voltage is about 0.8. If you go on the curve with 75 microamps, that's this curve right over here. It only runs into this at 1 point, and that's at 7.7 volts if you read the number off here for the 7.5 milliamps of collector current, given the 75 microamps of base current. This is our solution. This is very close to what we hand calculated of 7.3 volts and 77 milliamps. This is as accurate as my ruler is, but it's a way to visually calculate a result, or if we don't have a set of equations, but just simply a set of graphs. What we did with the load line with the diode is that we used the fact that when we're finding the X and Y intercepts, these really relate to the linear part of our circuit. This would be the case for the Y-intercept, where we have the Thevenin voltage over the Thevenin resistance. This would be shorting the base emitter junctions. And if we were to open the base emitter junction, that would be no current flowing. We just get the 5 volts of the battery. And likewise for the collector emitter, if we short it, that would put the 15 volts across the 1K resistor. That would again be this point over here. And then if we were to open circuit the collector emitter, we'd have no collector current, and we just get the battery of 15 volts. We don't have to write the equations for the transistor circuit, the linear part of it. Just simply find the Thevenin voltage and the Norton current, like we did for the diode. We could also solve this problem by hand using the Ebers-Moll equations in our equivalent circuit. But like the diode, we have transcendental equation, but now we've got 2 of them to solve, and that's even more difficult by hand. One way to do this is to use a math package like MATLAB or MathCAD, and in fact our textbook does that in section 3.2. It solves this problem using a math package. But actually this is the reason SPICE was written, that when you have all of these simultaneous nonlinear equations, the program will go after a solution for you. So let's take this same problem and solve it on SPICE by using the PSPICE program. Here's my schematic. I've numbered the nodes 1, 2, 3, and 4. Have a title, description of the circuit. My model, I'll call it MOD, and the type is an NPN transistor. As for the operating point, it'll give me the values of all of the node voltages in the circuit, and then also the model parameters. I just showed the model parameters here. Found I sub B, I sub C, VBE, V sub BC, and VCE. The base current is 74.5 microamps, and the voltage is 0.826. This is very close to what we had done with the load line. And again, our hand calculations, we assumed that this was 0.7, which again is in the neighborhood. We'll never get that exactly right. And then we had solved for this to be 77 microamps. We're pretty close to the actual answer by using our piecewise linear model, which was a fairly simple calculation. Likewise, for the collector current, I've got 7.45 milliamps and a voltage of 7.55. We had hand calculated this to be 7.7 milliamps and for this to be 7.3 volts. We can get in the neighborhood of an answer with our piecewise linear model, and then we could turn to SPICE once we've designed our circuit to get a more accurate answer if we need that. And this is the BJT as a circuit element.